Hello. Yeah. Hope I'm audible to all of you. So thanks to all for making it to this session early in the morning. Tutorial one from the set of 10 tutorials that we'll have today. So this is basically a track that's exclusively devoted to data science, and specifically it's explainable data science or interpretable machine learning, so whatever you want to call it. So the first tutorial, that's tutorial one, will be given by persistent systems. So there are three colleagues there: uh, Dr. Mukta Paliwal, Dr. Dataraj Rao, and Amog Tarkar. So these are the three presenters for this tutorial. And uh, I could probably go through the abstract of the tutorial very quickly. So the it's about responsible AI, and I think they will talk about how you need to adapt AI systems to build customer trust in transparency, accountability, fairness. That's the FAT model, is what I guess. I'm really excited about this tutorial. I think I'll have a lot to learn from this. So over to you, presenters. Thank you.
Thank you, Rama. Thanks for having us here. Let me quickly share my screen. Please confirm once you see the presentation.
Yes, we can see
Okay,
and hear you as well. Yeah, we can
okay.
see the slide and hear you.
Welcome to the first session of today's tutorials, and welcome all of the participants in this tutorial where we are planning to talk about how it is important in today's AI ML world to be responsible towards what we are developing, and some of the practices that we are following at Persistent when we are developing our systems. We would like to share some of our learnings with you during using this tutorial. We are three colleagues from Persistent planning to talk today and sharing our knowledge. Dataraj Rao, who is heading AI research. Myself, Dr. Mukta, I'm working as a senior data scientist, and along with me, my colleague Amok Tarkar, lead data scientist. We are planning to take you through the planned agenda, which is like this. So I plan to talk a bit of introduction on how it makes sense and why it is important to have responsible AI. And if before that, what do we mean by responsible AI? So understanding the principles behind using and making the AI development as a more responsible process. Then one of the pillars in that process is how we make or how we can make the systems fair and remove the biases when we are developing these systems is what I will cover. And reproducibility, transparency, and MLOps as a foundation of this our responsible system will be covered by Dattaraj. And data privacies with federated learning concepts will be covered by Amog. And we are open for any question that you might have towards the end. So please uh, be interactive as much as possible when we have the sessions open for the Q&A systems. So let
Uh,
me begin.
okay,
Yeah,
sorry, Mukta. I just sorry to barge in. So my feeling is whether the question is whether you want to take questions at the end of the tutorial, or if people have any questions, would you want to take them real time? I think there's a way by which people can raise their hands, and then you can answer that question if that works. Uh, so the
I
way to
would
raise
prefer.
your hands. Yeah,
Hmm.
please. Yeah,
So sorry. So I would prefer to have them at the end because when I'm sharing the screen in full screen mode, I can't see those hand raises and others. So I would prefer
fantastic.
to
Right.
take them towards the end.
Fair enough. So because there are three presenters, can we have the questions at the end of each presenter, so that if
Sure.
rather than having it? Yeah, that's correct. Thank you so much. Yeah.
Okay. Okay. So I'll open up the floor for the questions briefly before I hand it over to the next presenter. Thank you so much. So let us begin with what do I mean by and why we need responsible AI, as in putting up a little bit of context that is required here before we actually delve into the technical details of this topic. So now a lot of buzzwords. Data is the new oil, and AI is new electricity, right? We keep hearing all these kinds of terminologies when we do social media readings or these blogs or any of the technical papers that we start with, which is towards the area of AI and ML. But and on top of that, we all understand the potential that AI systems has brought up in our daily lives. But at the same time, with this great great potentials and the great usage of AI that is happening around us, it comes up a lot of risk that is coming due to some of these ethical reasons. And in the background, I purposefully have blurred some of the titles that I have kept in the slide. And the purpose is I'm going to give you some of these examples that how these systems has affected our life directly or indirectly. So you keep hearing about those biases due to genders and colors and any of the ethnicity group that comes up and creep up into the system wantingly or unknowingly. But what kind of impacts that these kinds of things might have on the AI systems in general, especially when we know that these large scale deployments, when we are making them, affect a large part of society. So let me quote some of the examples, and that is what is going to bring the examples and the context why now we are talking about responsible AI as a whole more so often. This is one of the case study from past, and it's one of the MIT PhD student named Joy. She actually have faced some difficulty during her own tenure, being a darker color skin female. She felt that the recent times, all the face detection systems by the big giants like Microsofts and IBMs, they have inherent bias in the way the systems are classifying the faces by gender and the color of the person. And she realized that the largest so basically on the screen what you are seeing is the correct percentage of classification by a group. So a darker male versus a lighter female, how is the percentage of correct classification by each of the system that was shown here. And you could see the largest gap is by a system by IBM, where we could see the correctness is having the wider gap between lighter color males and darker color females, and you could see the percentage difference is as good as 35%. So these biases she faced, and she produced a lot of good study, and I have just kept the source of the slides here. You may want to have a look at it, the details that she has brought up from her study on this topic. Similarly, this Apple Card has made a lot of waves on the social media with these things that a husband and a wife having similar kind of credit history and accounting systems, keeping all other features same, just because the gender of the lady is female, and then the score that is given or the credit limits that were offered to her was lesser than her husband. and and these systems and these kinds of biases are nothing new, but I would suggest that now people are talking more so because these are directly impacting the decisions that are taken by machines, by these AI systems on behalf of us. Similarly, this is again a pretty old system that was created to predict the repeat offense of the criminals, and there was high bias in the system that you could see based on the color of the skin of the criminals. So a lighter color person was given a lower risk, where the chances of actually his making repeat offenses are quite high, or actually that he made that repeat offenses number of times here, but the system predicted it otherwise. The point that I was trying to say is lot of these biases, cognitive biases, I can say, were already existing in the systems. So it is not new that that these things are talked about in philosophy or in social systems. But now we see that when we are developing our AI ML large systems, which affect the decision making at large, we need to be careful and be aware about when we are making these systems and developing these systems. This is about biases and fairness that I was giving few examples. This one is a quickly about the privacy concerns that we have. So this particular paper that authors have suggested that it is about that inverse mapping of the models. So given the AIML model and some of the externally provided demographic informations, the authors were able to produce the biomarkers, genetic markers of the patients, though they say that patient information is hidden and it has not been considered. But by this reverse engineering, they were able to figure out the patient's genetic information, which is very harmful. And it's a direct impact on the infringement of the privacy of the user without even knowing him. So the issue is, as we understand, AI is highly reliant on the training data and including information that may be personal or sensitive. It is not necessarily that people might have given explicit consent about the usage of it. And as I said, the impact is infringement to privacy of the people, and we have to make sure how we are able to make our system so that we can create that kind of a trust and transparency when we are developing those. So I was talking about the ethical issues that are arising when we are developing it. But apart from the ethical issues, there are uh, hidden technical depth in AIML system. So on the screen that you are seeing that when we are generating an AI or ML system or a software system at large, the ML related code is a very small chunk of it. And you could see that small black box in the middle of the picture, and rest of it is covered by, and all of us will agree as a data scientist that how much effort it takes to build a system as a whole, where the configurations, feature extraction processes, apart from all of this maintenance, monitoring, and serving the infrastructure that is developed, these are the larger code bases and they take a lot of effort and sometimes even the repeat efforts. So, in all, we would want to have some systems developed because we all know that this is a repetitive and iterative cycle that we prepare an ML model. Um, Having a reproducibility aspect into it and a pipeline that is more automated in the fashion is a very essential characteristics that we would want to develop when we are developing these things. So these are some of the considerations that tell us that why we need a responsible AI system, and that brings us to the pillars. The pillars, when I'm using the word pillars, they are essentially some of the principles, and these principles are widely been collectively been taken up by various researchers and practitioners at large when we are developing the systems, how and what needs to be taken care of under these each of the heads. So at Persistent, we include responsible AI in our model development processes in the steps of five. And these are accountability, reproducibility, transparency, security, and privacy. So I'll be talking a bit about accountability in the next sections where I'll give you a little bit of details here. And what do I mean by accountability is the points that I was talking just a little ago, that biases and systems are creeping because of various reasons, but we need to keep a tab. How do we do that is in order to bring and build the trust that the people of the systems create for us. So essentially what I mean to say is, why are we even caring about all these things? Basically, to create trust in AI systems by our customers or maybe the consumers of these systems. Because if we are not able to explain why we are taking some decision based on the prediction or the classification model, then we are not gaining those kinds of trust from the users of these systems. Basically, the credibility of the whole systems and the predictions out of it need to be weighing in such a fashion that we are able to use them for the larger audience. So, as the creators of AI systems, we have duty to create and deploy such systems who are ethically, I would say, ethically and technically fair. When I say technically, I mean to say easier for people to use, easier to develop, and fair for the society at large. So that brings and um, the taking me to start with the first pillar of the responsible AI framework that we have. And here I would like to brief a bit about the metrics and what do we mean by first bias, and how we define the fairness in the systems, and then we tackle. I'll show you a practical demo. How are we doing it practically for some example data sets? And before that, as I was mentioning earlier, right, that it's very important to take into consideration fairness issues when we are considering designing and engineering. It's crucial because these decisions should not reflect discriminatory behaviors towards certain groups or populations, as we see. Which is what is the point that I had spoken about in the examples that I have shared earlier. Now, when I say bias, what do I mean by bias? So there are certain kinds of bias, and a lot of work is happening in this field. And you could see there is a course from MIT, which is like AI biases and fairness, and a lot of details you could go and see there. This is open content, and a lot to learn from there. But I'm going to just give a little bit of quick context in respect of the time. So, what are the sources about of the biases in AI system that can peep in because of three major things? One is because of the training data. So, when since we know the prediction systems are largely dependent on how we train them using those training data sets, and the biases can arise due to these training data sets. So, this example that you are seeing on the rightmost side, you are seeing that it's a regression problem. So a red line is created when the data is considered as a whole. And you could see there's intrinsic group or heterogeneity in the whole data is explicitly giving those single model into an error prone situation. While in if you are able to see the heterogeneity in the data set, you could see that the slopes of the regressions are changing with respect to the all five groups. So this is kind of intrinsic nature of the data, due to which unknowingly the bias has creeped into the system. And when we are aware, so basically we need to be aware that there could be a bias in the system due to the way the sampling is done in the training data. How do we select our training data itself could be biased due to intrinsic nature of the people who are training the systems. So you could see that a lot of credit history algorithms in earlier days used to be trained in Western world, and they were a little bit biased towards the ethnicity of those kinds of people. So like that, there may be a possibility due to the selection of the training data itself. Now, similarly, in the reporting of the results, we could see that there is bias possibility, and which is what is visibly seen when we talk about statistical system or the results being shared. There is some kind of a personal bias creeping into these things. Similarly, Simpson's paradox is mainly that I gave the example about, where the heterogeneity in the group is what assumed as same, wherein actually because of each group of the person or the people or the training set in the data set, there could be an intrinsic difference in the nature of the data. Similarly, due to implementation, so at the time of processing of the data, there could be possible ways of the bias generation. And the third one is at the algorithm level, that's the way the algorithms are chosen or the way they are applied. There are certain kinds of biases creeping into systems. So this list is by no means exhaustive list. You could go at the said sources to actually check into the detailed list and possibilities of bias. But generally, when we talk about multiple kinds of bias, we would keep them in the perspective of how we define the fairness. So basically, any bias that we want to call it is essentially something based on how do we define bias, right? So fighting or maybe creating against these biases and the discrimination has a long history, as I was saying, in sociology and philosophy and psychology, etc. But as I just mentioned, it has become a larger issue and larger research area in the machine learning world nowadays. And how do we define fairness? It is simply is the absence of any prejudices of favoritism towards an individual or a group of based on their intrinsic or acquired traits in the context of a decision making. So basically, when we say that fair, we wanted to be inclusive of larger chunk that we are talking about, and the decisions those are getting applied on many of these people. So these are some of the applications, and they have base in statistical measures, how we define a system as unfair. This survey paper is a very good source that I have provided here. You should definitely check that out for a comprehensive review of how they are defining various biases and fairness matrices. Largely when and they are highly dependent on the kind of machine learning problem that we are talking about. So essentially, I'm taking up here some fairness metrics as an example, which are pertaining to the classification problems. But when we go into some kind of maybe that other problem domains of AI, for example, predictions and community grouping or clustering, the metrics will change as per the problem statement, and the solution approach will also be different. How do we go about um, treating the AI system as a whole, basically classification versus a clustering and an unsupervised problem? For example, this classification, when we have a classification system to train, these are some of the measures that are taken care of, and this is the beginning of understanding of how we can make sure that the systems are fair at large. And here you could see that typically we used to do in the statistical analysis as a true positives and false positives. How do we do a confusion matrix? Similarly, we would want to make sure that the precision and recall how they are calculated, and these are the statistics. We would want to make sure that the true positive, false positive, and true negatives in the context of the problem and the classification problem with respect to the group which is underprivileged. When I say underprivileged, I just mean to say that in case of gender, generally female group in context of salary as another things are generally underprivileged. For example, in case of the color of the skin of the person, the darker color skin persons have underprivileged group. And these statistics make sure that we have the classifications as balanced as much as possible in context of the definitions that I have provided earlier. So I'll take a pause here. I'm going to shift to the demo that I have, because these things, as we say that we have a lot of open source based tools available to handle some of these, and I wouldn't say they are again comprehensive to deal with all kinds of ML or AI problems. But the example that I've chosen is the classification problem, and this AI Fairness 360 from the IBM's research group is one of the such tools which is available in open source. And I'll quickly walk you through, but this is not the only open source tool that is available. You have FairML in Python. There are other tools available in other languages and supported by other big companies or corporates to support their initiatives in the direction of responsible AI. This I am just showing as an example. So basically, this is the demo of their AI fairness system. And here you have option of actually choosing a data set. So they have a sample data set, the compass study that I was talking about, the credit scoring, usual problems that we see due to gender or the color of the person, what could be difficulty in the credit scoring. And these are some pre-built examples that you actually go here, choose one data set, do next, and you're able to see how they are using these systems to generate it. So for example, here in this data set, as I was saying about, this was criminal repeat offense prediction system, where they just talked about how this is differing based on the classification of male female. This is one attribute. Race is another attitude, and you could see whether there is a bias. And there are multiple statistics that are provided, and each of them, the way I have provided the definitions on the PPT, are similarly available here as well. So you could read, understand, and based on that, you could take the evaluation. But you just check for the how and where the matrix is, the bias is creeping into the system. Either it is at the gender level or any other classification that you deem that is underprivileged versus a privileged group, and measure these things, and you can visually quickly check whether they are having any kind of biases or not. And then once you know that there is a bias, how to mitigate that bias is something, and there are different approaches based on the bias, the way you define your system. The simplest is this reweighing thing. You could see that if you have an underrepresentative sample of a particular underprivileged class, then you could reweight the classification problem, giving equal preference to both or more classes in the process. So here you could go and just check, and after the mitigation, you can see whether the new algorithm that you have used based on the pre-processing. So here we have just used one of the approach which is based on the pre-processing of the data. There could be an approach which is based on how do we choose the algorithm, or how do we pre-process the data. Based on that, the type of mitigation process will change. And this is the simplest one, where we are changing the training data. There we are making changes in the training data, and you could see that now we are not having any bias. 0 out of 4 metrics is having a bias for underprivileged group. Similarly for the race, after we have just done the mitigation of the problem. They have also provided on their demo page a notebook for you to play with, and with a lot of good description that this notebook is available. The same example that I was talking about, credit history, you use the same 5 processes. You are actually selecting what kind of a bias detection option that you want to choose, load your data, train the split the data set between train and test. uh, Essentially here you compute the metrics. Here this is like a binary classification problem, and you define which one is your underprivileged group and which one is your privileged group, just whether it is gender or age or any other parameter that you feel is underprivileged. Here you define that, and based on that you are choosing reweighing as a technique, the one that I have shown on their demo, and compute the fairness matrix. And in summary, the results are shown that there's no difference now between the mean compute outcomes between unprivileged and privileged group. Basically, you were able to mitigate the bias that was seen in the data due to the gender issues. So I'll take a pause here. If you have a quick question on the points that I had covered, I had to apologize. I had to rush through because we have shortened the time that was made available for us. I had to rush through it. I'm open for any questions
So,
that you might have.
hey, yeah, Mukta, thanks for making this quick. Actually, there is one question by Suresh Subramaniam, but I recommend let's take it at the end of my session because that will also cover this. And you can because I think I also cover that in the accountability piece when I'm talking. So let's do that at the end of my session, if you don't mind.
Sure, sure, sure. Thank you so much. So over to you, Dataraj,
Okay.
for the next step.
Yeah.
Yeah. Thank you.
Thanks, Mukta. I'm sharing my screen. Just want to take a check. Let me know when you see it.
Yes, we can.
Okay. So, hi everyone, this is Dattaraj. So, I'll talk about the second part after Dr. Mukta's focus more on bias and accountability. So, I'll focus on reproducibility and transparency, which are also very important pillars of our responsible AI strategy of any company. So, reproducibility talks more in terms of when you're building machine learning models. as you're building models, how do you make sure across different data scientists there are multiple preferences that each has their own preferred library, each has their own preferred way of programming, way of developing models. How can we standardize this? This is something as ML is growing, as every field is getting influenced by machine learning and artificial intelligence. This is becoming a major need in the market. How do we standardize, make your experiments reproducible? And just like you have in software, you have a DevOps cycle. How can we focus on an ML ops cycle where you are applying the principles of DevOps agility to machine learning so that your experiments are reproducible? Plus, you have the concept of an experiment. So typically, you have when you're doing software development, it's very deterministic. You check in your code, the CI/CD pipeline triggers, and your code starts building. But in ML, there is a concept of an ML experiment. You have to know the data, the source of the data, how you have to do a lot of, like Dr. Mukta had shown, a lot of effort is spent by data scientists, not in the actual algorithm development, but in actual data cleansing, feature engineering to actually build a model. So reproducibility becomes very important there. And then, like we had these examples where the model actually had bias. I mean, no company intentionally wants to introduce a bias, but because the data has the bias, that comes into your model. So how do you check for that? Can you use some way to explain your model, find out if there is a bias? So those are the things that typically are into the transparency pillar. So let's start with reproducibility. Now, like we said, with the modern ML ops pipelines, it's more than actual just building an algorithm. So there are four, at a high level, at a conceptual level, there are four things that a data scientist typically has to focus on. Data management, where you have to look at the data, cleanse the data, make sure the data is good quality before you use it to build a model. Of course, the core model development, then deploy, taking the model. I mean, you have to choose between different models, do hyperparameter tuning, and then the selected model, you are deploying that to production. So you need to have a system. You cannot be building a new deployment system for every model. You need to have a system. And today, the most popular way of deploying models is using microservices. So microservices based system, where the model can be deployed as an API and can be invoked through a client application. That is very important. And then when you do the deployment, there are a lot of other consideration. You want to do things like A/B testing. In fact, now mature ML organizations are even doing multi-arm bandit. You're trying multiple models at the time and using almost concepts of reinforcement learning to make sure you get the right model to the right customer base. And then overall, a model lifecycle becomes very important. How do you track what is the version of the model in production? And when a new model comes, how do you compare them? So there are tools, there are a lot of open source tools that have matured in the recent years. Things like Open ML Flow, PyCaret, which address each of these stages in your ML development cycle. And I'll cover some of these. So I'll focus on DVC, which is data version control, then PyCaret, and at the end of this half an hour, I'll show a demo of a reproducible ML pipeline having some of these tooling like PyCaret, ML Flow, and then using some of these methods to deploy a model and deploy a model to a model registry. Now, as you know, there are a lot of these cloud offerings like AWS Data Studio or Databricks or SageMaker. Now, these systems are kind of inbuilt. They address all these four stages. So even if whatever the tooling you use, I mean, you may use Spark or you may use regular Python, TensorFlow, PyTorch, the patterns remain the same. So what I'll focus is more on the patterns of each of these four stages, because your technology stack may be diverse, but as long as you can focus on some of these patterns, I think that can be reproduced. These patterns can be reproduced in any programming technology stack, and then you can with your ML ops cycle should kind of try to focus on some of these reusable patterns. And let's talk about some of these patterns. So one, in data management, definitely a data ops pipeline. You would want to have a pipeline where you want to clean data, especially if you're not getting quality data. You want to do a lot of feature engineering. And now a pattern which is popular is a feature store, where you have fixed rules to clean your features and make those same features available both for training and for inference. A version data catalog is highly recommended. We have seen the stage where we have CSV files to build models, but then you have to have a version control for the CSV file. So our tool like DVC, data version control, and again, this is just a pattern data catalog. You can use DVC. You could use a different tool for this. Same goes for all the patterns that we'll talk about. But DVC, what it does is it puts an encapsulation layer or an abstraction layer in front of your data. So your data could be in S3, your data can be in Google Drive. You access it the same way, and it will manage the versions of the data. So that's pretty popular. Data quality is very important because you want to make sure your data is complete, accurate. You want to clearly know if there are missing values and what to do with them. Model development, AutoML is becoming very popular, where instead of you manually training multiple models, you want to be able to have a tool which can automatically use the same data, train on multiple models, and give you a list. So we'll see an example of this with PyCaret. And now we are seeing a lot of growth of low code and no code ML tools. So things like PyCaret, which are low code, where the data scientist has to write minimal code, just set up the experiment, and the system behind the scenes does a lot of the groundwork and gives you some clean results, including plots. And then for production deployment, like I said, we do want to look at how A/B testing can be done, multi-arm bandit. So there are tools like Seldon, which can help in this. And for the life cycle, there are patterns like model registry, monitoring, and we'll see model registry in ML flow. So you want to be able to version the model, keep it in the registry, and then make sure you can retrieve the right version for the right production system. So long story short, these are the four stages of your MLOps pipeline. Typical stages in an MLOps pipeline. And there are different established patterns in the industry, and you want to whatever the tool you use, you want to be able to have some of these patterns to address specific problems that you have. So let me take an example. This would be your typical, a very your current ML cycle. You will have an ML development environment and a production environment. A development environment is where you will do your data preparation, your model development, testing, and validation. And then once you're the data scientist, so this will be typically for the data scientists. Once your data scientists are satisfied with your statistical performance of your model, you would want to deploy it. So you would want to have an environment, either a cloud or on-premise, where so this is typically in today's world leveraging microservices. So you could use something like Kubernetes to package your model as a microservice on Kubeflow and deploy this. So you have your ML model running in production, and you have this logging service which comes with your production environment. So on the data science side, you typically look at the statistical metrics, like you look at the confusion metrics, you look at the area under the curve for the ROC curve. And then on the production side, typically these metrics, if you look at Kubernetes, you can have tools like Prometheus to actually log these metrics, and Grafana to visually plot them. These metrics are typically service level metrics, where they will tell you if your API was down for so long, of 24 hours, how many minutes or seconds it was down, and then how much data came in. I mean, how many API requests came in, what was the size of the request. So these are more like the service level monitoring of the metrics. So this is typically, I would say, how a traditional setup would look like. Now, let's see how we can add reproducibility to this. And again, I'm just focusing on patterns. So some patterns to add reproducibility to this setup. Number one will be a data catalog. So instead of you just having these CSV files with -v1, -v2, let's have a data catalog where, just like Git, you are managing versions of of your data source. Now this can be either done at file level, like a DVC, or if you have something like a Snowflake, which is more of a SAS CRP, you could actually do versioning of the data at the SQL level. So this query would give you version 1 data, this query would give you version 2. Now Snowflake actually has a time travel feature. You can actually write your data catalog at a temporal level. So you can say, for data collected till this date, give me this as version 1, and till this date as version 2. So so modern tools have a lot of advanced features to do temporal analysis. But for this experiment, we just use DVC to version files differently. And DVC, like I said, will give you an abstraction layer. So I have my files on Google Drive. In this demo, I'll pull them from Google Drive and show you the different versions. Model registry is another popular catalog. Like once the model is published, you're happy with the metrics, you want to push it to the registry. And then at the service level, now you are looking at uh, service level monitoring. Now we can add some transparency to this, where along with the service level monitoring, you also want to monitor for things like data drift and concept drift. So what happens is, your model, once it is deployed as a microservice into production, it has been trained on some representative data set that you collected, some version 1 of the data set. But now over time, the situation changes. For example, with COVID, the pattern of data was totally, especially in retail side, was different. A lot of people were working from home. There was more internet traffic. People were buying at regular office hours because everybody was at home. So because of these changing patterns, you would see your data that you used to train the model is no longer representative of the production. So in that case, you will see like a decrease in accuracy of your model. So this will be the relationship between the target and your variables would change. So this will be a concept drift, and you can also detect this by data drift. So if there is a like when you're working from home, there is a big increase in bandwidth during the day hours as compared to when people were in office. For if you are an ISP, so you would want to so you will see a change in distribution of the data. So you also want to monitor the data drift in production along with your service level metrics. And then you also want to have some sort of an explainability. Now, explainability becomes very important for transparency, and this can be done at three levels. So it can be something that when you select an algorithm, if you're building a model, you may want to select a more interpretable algorithm, right? Random forest. So something like a tree-based algorithm, which can be inherently explainable, you may want to select if explainability is very important, or you may want to look at post-hoc explanations, where you may select the best model like an XGBoost or even a deep learning model, but then you want to have some system like Lime and Shep to actually provide explanations. Now, this is where in our demo, we'll see an explanations that are generated on the model, which are part of your MLOps cycle. So we highly encourage that have this as a pattern where when you have an MLOps cycle, you want to also include explanations. And in your report, make sure that some of the results of these explanations and the fairness studies that Dr. Mukta showed earlier, those are also included in your MLOps cycle. So, and then the third level where explanations come in is at the inference level. When you are actually, once your model is deployed, you're making a prediction. You want to do a local explanation at that level where you want to know why a particular prediction was made. So in that case, it gets into more complex things like how can you explain an individual prediction? There are even things like counterfactual, where what if certain values change? Can you account for the change in prediction? So things like that. So it can be very detailed that way. But these are the three levels where you want to at least have some sort of an explainability as a sanity check in your MLOps pipe cycle. And last thing, what Dr. Mukta covered in detail is basically the accountability piece. Now, this is, in my mind, the very most important piece. I mean, these are reproducibility, transparency, these patterns you can apply using tooling. But accountability is something more of a culture change for the organization. This goes back to the Dr. Mr. Subramaniam's question also. Like, who is accountable for this? I mean, basically, if you are a vendor, you would want to have best practices to include some of these reproducibility, transparency into your MLOps cycle and have some sort of an audit mechanism when you're delivering an AI. When you have your MLOps cycle, you would want to provide an audit mechanism when along with the model, you want to provide why some decisions were taken, what was the data set that the model used for. So ML tool like MLflow can give you a nice audit report where it will tell, and I'll show an example of that audit report where it will tell you what are the charts that accuracy charts that came out, what are the fairness studies, and then why some decisions were taken. And then the committee also has to decide, like once you do the monitoring in production. So when the production monitoring is done, if you detect a concept drift or data drift, now typically it's a gradual transition where this data drift and concept drift happens, and your accuracy starts dropping. You want to decide at what time you want to trigger a retrain. So if the data accuracy falls below, say, 80% or 70%, you want to trigger a retrain. So that also should be designed by a human in the loop, and that's what the AI committee would do. So I would say AI committee is definitely recommended for a vendor who wants to make sure that your process is has all the audit metrics, and also for the customer who is ultimately going to be responsible for the output of your model. Whoever is ultimately responsible for the prediction that your model is making, they would want to set up specific requirements for fairness and bias for your ML model, and that will be something managed by the AI committee. So, in a nutshell, these are the three uh, initial pillars: reproducibility, transparency, and accountability of responsible AI. And now I'll show a demo or a notebook demo of how some of these can be incorporated using tooling into our MLOps pipeline. And then Amog, in the last section, will cover the other two pillars, security and privacy, which are also equally or probably more important. So let me jump to the demo. So this is a Jupyter notebook I have, where what will show is just doing a check. You can still see my screen and I'm audible, right?
Yes, Rudra.
Okay, cool. So let me walk through this. So here, what we'll show is we'll show basically a couple of we'll show focus more on the data science cycle. So this is for the data scientist persona. So we'll use a data catalog to load data from an external system like S3 or Google Drive. It could be your own private VPC or Azure. And like I said, here it will be more of file based, but it could easily be a Snowflake database. And you load data into a data catalog, load a particular version of the data, I should say, build a model. So we'll use a low code tooling called PyCaret in Jupyter Notebook to build the model. We log metrics to MLflow, and then once the model is ready, we are happy with the metrics. We'll publish the model to model registry in MLflow. So we'll use MLflow for both logging your metrics, tracking your experiments, and also for model registry. Now you also use DVC to manage your model versions. So it's kind of like I said, there were multiple toolings. You can choose whichever is the best, and there could be a better model registry in future also. So, and then the other part we won't cover today because of lack of time, but it's important to know, like once you deploy the model, you could use a tooling like Seldon to package your model as microservice and deploy it. Once the model is running in production, it could feed from a live data, which could be a live data stream. And then there are tools like Alibi Detect, which can detect outliers and drift in your data. And it can look for concept and data drift. And then once a drift is detected, based on the AI ethics committee, the decisions made that at this point I will trigger retraining, we would send it back for resampling, where they will go back to the data catalog. And this probably would be more of a manual where data scientists would need to spend time to figure out, resample the data and say, okay, this data looks better, and then use that as a new version of the data. And the process begins again. So this is one view of the data science and the MLOps cycle using some of these patterns. And so let's have a look at it now. So this is my DVC code. Uh, so instead of loading a CSV in Pandas, it becomes little, it adds a few lines of code. So what I'm doing here is I'm setting a version for, say, this is one of the, going back to the fifth version because that was my original data set. Uh, and I'm calling the data set, I'm just giving it a data set label version 1, and let me load that data set. So I'm loading that. So now you can see here the original data set is actually in Google Drive, but I'm just loading it using DVC, and DVC is just giving me a gate interface to that. Now, this data set is basically from Kaggle. It's from the Analytics Vidya loan prediction competition. And here we have this fields like gender, married, dependence, education, and the target is the loan status, if the loan was approved or no. So multiple features like loan amount, credit history, etc. And the target is loan status. We are trying to make a prediction. Now you'll see a lot more categorical features here. A few numeric features like applicant income, co-applicant income, etc. So and then what we'll do is for the categorical features, like just do a plot of how the outcome changes based on some of these protected features. So we saw in the previous session by Mukta where gender and married would be a protected feature, and would we want to kind of would we look at uh, how our decision influences by that. So this is a pure just a direct plot that we did to see how the variance is, and we can see though there is a less number of females, but the distribution seems pretty even, where you can say for the loan status, the number of approvals and rejections look pretty even. Now, this is visually. We can do the same thing using Fairness 360. So we can look at AI Fairness 360 and calculate matrices. So these are the two matrices that Mukta talked about: statistical parity difference and disparate impact ratio. So I'm importing AI Fairness 360 library here, and using the gender and using gender as the field, I'm calculating the statistical parity difference. And you can look at the IBM website. It has very good definitions of each of these terms. So statistical parity difference will just tell you between the two groups how much is the statistical parity, the difference, and this should be between I think this should be between -1 and 1, and a smaller value close to 0 should be good. So, so this value is pretty good, and disparate impact ratio should be more close to 1, and 95% is pretty good. So this data set seems to be pretty fair. Now, what I'll do is, because I have access to DVC, now instead of loading a new CSV file, I'll just change the version 2 and move back from 5, I'll go back to 4 and load a new data set. So hopefully this will be loaded from Google Drive. Now, these were the original charts where you will see the distribution of the loan status. Let me run this on the new data set. And now you see there is a stark difference in the distribution. Now, a lot more females loans are getting rejected compared to male. So this visually looking at this sets a trigger to me. So if I'm a auditor or from the AI ethics committee, if I get a report like this, that my previous data set had a much even data distribution, and then my new data set, the distribution is changed. Now this is a red alert that okay, something is going to be wrong with this data set. There may be a fairness issue. Now let's go ahead with it. Let's consider this. Go ahead and see how this will affect. Now, now before that, let's just run the statistical parity metrics also on this. So I'll run this metric. Now you can see that the metrics have changed. So there's a minus zero point 0.4. So minus, I think it was minus zero point 0.1 to plus zero point 0.1 is better for statistical parity difference. So minus zero point 0.4, that means there is a bias in the data set. Similarly, this one has become very less. From zero point 0.9, it became 0.35, the disparate impact ratio. So definitely there is a bias that we are seeing in the data set. So from the data catalog, what we saw, we loaded two different versions without even having to look at files. We just changed the version name. We loaded two versions. We could compare the distributions. So this was one of the patterns of data catalog, and then using fairness metrics to look at the distribution and quantify. So first, from a chart, you can see there is a bias, and you can quantify the bias. Now let's go forward. What we'll do is we'll use ML flow for logging this experiment. So I know there may be a bias in this data set. So let's see how my data set performs. Let me go ahead and build a model. So I'm going to connect to ML flow. So I have ML flow running on one of the servers, and I've created an experiment called Chords Comet demo. So I'm going to run with this data set on that demo. So first code, this is pretty just a code to connect to my experiment. Uh, so what I'll do is these charts of data distribution, I'll log them. So with ML Flow, you can log your matrices as well as you can log charts as artifacts. So I'll do that. I'll go and log the fairness matrices. Uh, I'll do the pre-processing of the data here. This is standard pre-processing, dropping NAs, doing some of the data normalization. And for this demo, I'm just building a simple random forest model. One of the reasons because it is inherently explainable. You can do way more. Like you can use something like PyCaret to actually build a lot of do an auto ML, do a model comparison. But for this one, I'm just doing a straightforward uh, random forest. I'll collect the confusion metrics, and then I'll log the confusion metrics, and then I'll generate explanations for this. So what I'm generating here is using SHAP library. SHAP is a game theory based explainer. So it's a post hoc explainer. So it will take a model and run game theory based explanations. It will allocate credit to each of the features based on the result, and it will generate this. So this is a global explanation for the entire model. I'm trying to see which features are important. Now, if you look at it, it says credit history is important, which is great, which is ethically correct. But it says gender and married become very important for the second and third feature. Now, this tells me that there's a bias. So we saw that there was a hint of bias from the fairness, and now after building a model, that bias from the data went into the model, and the model that I have tested for explainability now has a bias. So this is an example. We saw the data loaded from the data catalog had fairness has bias issues, and that bias when I used it to build a model, that bias directly featured here. So now let me log this model and end the experiment. Now I could save the model to DVC also, but I would prefer to save it to ML Flow. So let's go to ML Flow now. So in ML Flow, I'll go to this category of experiments. Now there are two experiments because I actually ran the same ML life cycle with the earlier unbiased data set. So let me look at that first. So this is the unbiased data set version 1. And you can see these are the metrics that what MLflow does is this is the kind of audit I was talking about. You don't need to run this as a Jupyter notebook. You could have run whatever steps I did as a Jenkins job. So as a Jenkins jobs for a new data set, I could just follow these steps, do the data cleansing, run the feature engineering, and build a model, and then give a report like this to the AI ethics committee or to a more of a manager. You can give a report like this in ML Flow saying, okay, this for this data set, first these are the data set metrics. This is the disparate impact ratio, which seems pretty good. Statistical parity seems good. Once you build a model, these are the model metrics. Test accuracy is zero point 0.8, which is good. Test FN score is 0.86, which is good. These are the charts if you want to see the data distribution. This was the original data distribution we saw. There's a very even distribution of male and female genders. And then this is the model. So I have also logged the model. Now what you could do here is I could register this model. So I can go to so MLflow has a model registry where I can say, okay, for the loan prediction, let me register this model. So now I can go to the models available here. And this is the latest version, version 5 of the model. This is in the registry. So now instead of giving that model as a pickle file, the model is available into this model registry. All I have to do is call the registry using MLflow API, and it will download the right version of the model and use it. So now everybody, wherever you are experimenting or deploying, you use the same version of the model from the registry. So this pattern of model registry really helps to standardize and achieve reproducibility, just like the data catalog did for the data set. So the last thing what we look at is these two experiments that we did. So we did on dataset version 2 and version 1. Let's do a comparison. So so this is another thing what ML4 can allow for. So we can look at this and let's do the comparison. So you can see this was the dataset version 1, which we saw did not have bias, and dataset version 2, which had bias. So you could clearly see now compare the disparate impact ratio is 0.35 to 0.958. The accuracy you can see has improved. So the bias data set did give you a better accuracy, but it had a bias. So this is the human in the loop decision you have to make. You may get I mean, the 0.83 is probably small, but you may even get a data set with a very high accuracy. But then, are you ready to account for the bias? Because that model bias in the model has translated to the bias in your bias in the data set is translated to the bias in the model. And yeah, so and then what you could also do is look at this particular bias data set, and you can see the explanations here. So here for this bias data set, gender, like we saw, was an important consideration. But if you look at the older, the first data set version 1, and if you look at its SHAP explanations, here credit history, education, property, these are the factors, features it considers for making a decision, which make now this is what the AI ethics committee would do. Okay, this seems more ethical, so I would approve this model, I would not approve that model. And because you have a model registry, they can decide this model is going to production, this model is not, this model let's hold and rethink the data set that was used to build. So this, so as a vendor, I mean, and coming back to the same question, you would want to enable your ML pipeline to have these patterns where you can check for fairness, bias, make these metrics available as an audit, where a decision maker, it could be your decision maker as a vendor or your customer, could make a fair decision based on this. Because when Dr. Mukta showed, the first definition of fairness was fairness through unawareness. You don't really know that your data set is biased. Nobody willingly is going to introduce a bias model, but because of the bias in the data, uh, the the unfairness comes into your model. So you want to check your data set, have the right metrics in place, give an audit report like this where you can track your metrics, track your fairness charts, and then once the model is ready, do again a cross checking to see how the explanation, do a global explanation chart like this. And SHAP is just a tool. You could use any other tooling to get the IBM also has multiple libraries. You can or even Microsoft has libraries for checking these the feature importances. You can check feature importances, see which features drive your model's decision, and then the ethics committee can decide, okay, is this model good enough to deploy to production, and that becomes the human in the loop decision. So this is kind of and then I didn't get to PyCaret, but PyCaret would actually just make it easy for you to build a ML model compared to just sticking to random forest. But it's a pretty popular low code. That's another pattern, low code machine learning. So these were some of the few patterns: data catalog, model registry, fairness metrics, explainable AI. That we highly encourage you as part of your responsible AI system. Whatever tool you want to use, you would want to use this into your ML pipeline, and whoever is the decision maker, you want to present this audit report so that they can take a informed decision free from bias. So that was my part on reproducibility. I hope, Mr. Subramaniam, I hope your question has been answered. So since we are running out of time, I'll hand it over to Amol. And if there are more questions on this side, let's take it at the end of the session. We will be there after the session ends for another half an hour. We can take more questions. Somebody wants to stay back, but let's switch to the next part, Amol.
Thanks, Satyaraj. Um so let me share my screen. Meanwhile, I would suggest Dattaraj and Mukta, you could look at the chat screen as well as the QA screen. There are some questions I see, and maybe you could attempt to answer them in the chat as the session is going on, or we could also wait for the uh, wait for the session to end, and then we can interact with the questions. So
It suggests, Amog, we shall take them towards the end. We will take them one by one so that each question is
Yeah,
answered, and we will be staying back till then. So don't worry, and we will try to answer each one of them.
sure. Um, Mukta, is my screen visible?
Yes, yes, Amog.
Okay. So, yeah, in this section, we'll just switch gears to how do we do machine learning on sensitive data, where the privacy and the security of the data becomes more important. So there are multiple techniques in this space, and let's just try to cover a few of them today. Starting with federated learning. So, what is federated learning? Let's get
Amog,
to that.
sorry,
Yeah.
I see a question on the screen.
yeah. Amol, your screen is just showing one question. I think the wrong part is shared.
Okay. Let me try to share my screen again.
So I think it's a question that's getting shown on the screen, which has been asked by Nanda Kumar. Uh, and since it is unanswered, it is showing on the screen. Just
Okay.
share again once.
Okay, share again. Yeah,
Okay.
now it's fine. Now it's fine.
No,
Go ahead.
it's fine.
Yeah. So in this section, let's quickly cover how do we do machine learning on sensitive data. So the first technique over there is federated learning. So in traditional machine learning, the data is often aggregated to a central location, and we train machine learning models on it, and then deploy it to applications. Now we have observed that with more data, the models usually get exposed to more diverse data set and get more. They get very they improve over the performance, and the diversity of the data is what makes the machine learning models learn more patterns and perform more effectively. Essentially, this data, especially in case of sensitive data, is not often at one place. It's often siloed across multiple geographies or multiple organizations. Like in this case, some of it could be in America, some of that could be in Asia Pacific or the Europe region. And with stringent privacy regulations and security concerns with aggregating so much data, it's very challenging to put together all this data just for the purpose of machine learning. So we need to find a way around how to work with the sensitive data without really aggregating all of it together. And federated learning allows us to get there. So first thing is that it moves machine learning training closer to where the data is. So essentially now we'll not train only one model, but instead we'll be training local models at every location. But when we do that, we need a system to kind of combine the insights from all these models together into one common model. And that's what is the protocol of federated learning. In federated learning, we start a training round by the coordinator where a base model is created, and then that model is shared with each of these local regions. We call them parties in federated learning. So each party then trains their local model, and the updated model is then shared back to the coordinator. This coordinator uses fusion algorithms to combine the insights from all these local models to put together and make a better model. Now, this is not a post-training process. It's like a ongoing training process. Like if we have already trained models, we combining them simply would be an ensemble. But in federated learning, essentially the training is spread into training epochs. You can think about it as uh, if you want to do epochs multiple times, that's how we train models. In the same way, these federated learning rounds need to be repeated multiple times so that uh, the fused model gets back to the local setup and is exposed to the data from each of these regions. So we need to repeat this process multiple times, and it's kind of a collaborative training experience to get our final trained model. Now, a big advantage of doing it in this way is that firstly, the data is not shared or aggregated at all, so the data remains safe. It's not aggregated, so the chances of it being leaked and uh, misused is mitigated. So that gives us a security benefit. It gives us the regulations benefit because the data is not moving out of the regions, as well as it's giving us privacy benefits to some extent, and they can be improved further with other privacy preserving techniques, which we'll be covering in the second part of this session. So, firstly, federated learning is useful when the data is not able to be aggregated together because of either privacy concerns or legal concerns or maybe competitive market dynamics. Or it could be a second scenario wherein the data is too large to be, like, for example, if IoT device is generating 1 GB, 2 GB of data uh, at every single location, and that much data is extremely costly, measured in bandwidth to be aggregated together, we could apply federated learning there. So a few thumb rules of federated learning is that firstly, if your data is it can be aggregated, you should go for traditional machine learning techniques. For federated learning, there needs to be a condition wherein it cannot be aggregated. Secondly, the cost of aggregating all this data is really prohibitive. And thirdly, we need to be convinced that the model will improve with more diverse data. In federated learning, we have two types of federated learning: horizontal and vertical. Horizontal is essentially when the data frame can be actually sliced horizontally, that is, features as well as labels are available at multiple locations, and we just want to combine models together that way. Or vertical federated learning, wherein the data frame is actually sliced vertically, that is, not all the parties have the labels. This example in this particular vertical federated learning could be something like a e-commerce website and a bank. The e-commerce website might have data about what exactly is the wish list of this particular person, but will not have details such as income information or credit history. So let's horizontal federated learning, we have kind of two types of setups. First is a cross-device setup, wherein we could have hundreds of devices spread across multiple regions, like hundreds of laboratories in UK and US could collaborate using federated learning and share all their insights without sharing their data. That would be a cross-device federated learning. Or we could have a cross-silo federated learning, wherein there is, if we are trying to train a model for a rare disease and the data is present across community hospitals and cancer treatment centers, but the data cannot be aggregated because of privacy or legal concerns. So when we come to how do we go about doing federated learning, there are multiple algorithms. One of the most popular one is called federated averaging. It's basically weighted averaging of the model parameters while taking into consideration number of data points which are present at every client node. If we go for iterative averaging, we are averaging the parameters of the model without taking into account the number of data points. So we could make use of federated averaging or iterative averaging, or one of the more advanced algorithms such as Fed Plus, which kind of tries to make a local copy and blend together with the global model. I would encourage you to read more about these algorithms on GitHub. And a few libraries which implement this are IBM Federated Learning, Flower Framework. These are very good libraries which allow us to actually work on federated learning. Let's quickly see how IBM Federated Learning can be used to train models in this fashion. I've switched to my web browser. Can someone confirm if my web browser screen is
Yes,
visible? All right.
yes, go ahead.
Thank you. So in IBM Federated Learning Library, it's the same paradigm. We set up an aggregator, which is an aggregator script, and then parties join in. Over here, let's try to build an MNIST classifier. It's a classifier for handwritten digits. We'll set up the aggregator in this notebook, and the data is For this tutorial is being generated in this notebook, but essentially this is what will be present at every party. So essentially, when we see over here, we have around 200 data points for training at each party. So the next thing is that as an aggregator, I'm training the base. I'm kind of building or compiling together a base model. Over here, it's a CNN model with some convolutional layers and max pooling. Now this model will be the base model, which will be shared with the parties. Essentially, then from the aggregator stack, I'll just start an FL connection, and then the parties can join in, and we can then begin the federated training rounds. So over here, for doing this, IBM Federated Learning has a config kind of a methodology wherein there are YAML files which can be edited for what is the fusion algorithm, what is the hyperparameters, how many parties will be joining, how many rounds we want to go on, and so on. And so this configuration will be used for triggering the aggregator script. And once we have the aggregator started, then we can switch over to the parties. And from the parties stack, essentially there'll be a similar configuration file, and we need to configure the data which we have. So over here, there's an NPZ file which is being provided to this notebook, and a specific local training handler, which is just telling how exactly to fit this particular data on the model which is being shared. And we register this party. For registration, of course, the IP address of the aggregator and the connection details which need to be provided. And once we join here, then essentially the aggregator controls the training rounds. So over here, when we say start training, it will essentially start training on the parties. So simultaneously, both the parties will receive the model and then they will start training. Over here, as we see, there are 3 epochs running, and after every like 3 epochs, this model is essentially the updated model is being shared back to the aggregator, and the aggregator is fusing it together and again resharing it. So in a decentralized way, we are trying to train these models. And as the rounds progress, we can see that the accuracy is improving and the model is actually getting better. So once we are done training, we could actually plot the results and see that the accuracy is improved. In interest of time, let's switch back to the screen. And continue ahead. So another example of similar type of training is a case study which we had done at Persistent. This is the endoscopy image classification dataset called Quasir dataset, which had around 8 classes for various endoscopy, anatomical, and disease scenarios like polyps. And what we observed was the dataset could be split on the resolution of these images. So there was a party which had a resolution of 576, wherein we could see that class 7, there are very few classes present. The number of data points are very less. In 1024, we actually have class 0, 1, and 6 missing completely. So essentially, if we were to use only the data available at that particular party, we would have got a very weak model because it's underrepresented in certain data points, as well as some data points are completely missing. But if we try to combine a model and try to train it using federated learning, as we see as we see in this particular chart, we can see that each party, the loss curve is slightly different, but as the models are being fused together, the insights are being shared and all the models are actually improving. The global model, as we see the red line, is the best amongst these all. So we achieve a common accuracy of around 85%, and individually we were getting really weak, like we couldn't even cross 60% on their own before. This is another example wherein we have a segmentation example wherein there was a data set of identifying these polyps and with a segmentation mask. If we train with only the data available at one hospital, which is say the Norway hospital with 1000 images, we were getting a pretty weak mask. But once we started federating it together with the Spain hospitals without sharing the data directly, we could see significant improvement in the model which could be trained. So there are these very popular libraries for federated learning, IBM Federated Learning, Flower Framework, PySift, Fate. I would highly recommend you to read more on that. Let's try to get into the privacy concerns arise with this. So Firstly, as we saw, federated learning is a collaborative technique, and so the data as such, because the raw data points are never shared, so that's safe. But there are still adversarial attacks which could happen on the models. So from the adversarial attacks, we could actually try to get information such as a particular data point is there in the training data or no. And to prevent such attacks, we can mitigate them using techniques such as differential privacy or homomorphic encryption. The second type of challenges is actually about the integrity. Like every collaborating party has to follow what exactly is told. They should be using the right data. They should be not tampering with the training code and so on. So for that, for preserving the integrity of this code, we have techniques such as confidential computing. So when we are trying to understand privacy preserving machine learning, we need to go in three steps. First is, what does this technology offer? Second, how does it apply to machine learning? And then how exactly it can be applied to federated learning? So differential privacy is a concept wherein we want to protect the privacy of individuals, and we want to get statistics at a full group level. For example, if you want to ask a very sensitive question to our entire company, that how many are really considering a job switch, that would be extremely sensitive to ask directly. So to protect the privacy of individuals, we can collect the same data from by using a technique such as differential privacy. One very rudimentary example is, before answering this question, maybe we could give them a coin. So if the coin comes heads, they have to tell the real answer, and if the coin comes as tails, they need to just flip the coin again and tell what the coin says instead of their real answer. So essentially, what we are trying to do over here is that the heads, which is the real answer, uh, like if I'm considering a job switch or no, I could give that real answer when it comes as heads, or when it just by chance my coin falls as tails and then again it falls into tails, then I will be answering the same thing. So there is ambiguity to how my individual data point can be assessed. But overall, as a statistical level, we know that the amount of noise which we have added to the entire system is finite. It can be measured as like 25% of the times it will be because of this coin being flipped. So we could try to at an aggregate or statistical level, we could try to remove that and get to an overall percentage of how many are really considering a switch. But what this really does is protects the privacy of individual data points. Another way of understanding is this beautiful slide, which is by Nicholas Papernote and Ulfar Ellingson. Uh, in this slide, as we see, each data point could be a dot or a M, and the bigger picture is over here as we see a Mona Lisa picture. So individual data points are this dot and M, and when we try to apply differential privacy, we are trying to flip each of these data points by a probability of 25%, and we get a much noisier Mona Lisa, but still, as a pattern, Mona Lisa is emerging quite clearly. So that's the technique which you need to apply, and this noise as such protects individual data points, and that could be applied at a raw data point, or it could be in our case applied to the model parameters and not let it overfit for certain data points. Like if there is no differential privacy applied, often we get overfit models like this, wherein just by analyzing the training data of members and non-members, we can see that there is a big gap. And when we try to use differential private algorithms, we are trying to train models which actually try to focus more on the pattern of what's really supposed to be taken at a group level and not remember every data point. So there are many techniques for implementing differential privacy, like IBM's library is there, Opacus is there. Specifically, when it tries to apply to federated learning, we need to protect only the weights which are being shared to the federated server, because that's the only thing which is getting transported. The private data is never shared in federated learning. So differential privacy could be applied at every party as it is trying to be sent out to the federated server. So this works well when we have uh, many of these parties collaborating, because the noise as such gets nullified. When there are very few number of parties, we need to control the amount of differential privacy which we are applying, and that's controlled by a parameter called epsilon. And when we say epsilon is 0, we get zero utility from it. It's completely noisy data, and if we increase the epsilon to a very high value, we might get perfect utility, that is as good as no noise applied, but we lose out on a lot of privacy. So we need to strike a balance between which epsilon value would work well for the example which we are running. that's the first technique. Let me quickly cover the second technique as well. Homomorphic encryption is a normal encryption technique. Usually, when we go to the ciphertext, those ciphertexts are not that useful for doing any more mathematical computations. Homomorphic encryption technique is such that the ciphertext can still be operated upon, like you can perform addition or multiplication of ciphertext. And essentially, in a rudimentary way to understand it, is a simple example like this. If an encryption scheme is there, such as it's just going to multiply by 2 and divide by 2 at the time of decryption. Essentially, in plain space, we wanted to add 3 and 5, but we don't know exactly how to do addition. So we could send 3, encrypt it, it becomes 6, and that is being sent to the cipher space. 5 becomes 10. In the cipher space, the server can just add these two numbers and get 16. The server doesn't understand anything about what the real number is as such from this 16, and it can do this computation and send this result back. And this result, then I can, because I know how to decrypt it, I can get my value as 8. So essentially, when we are trying to fuse models, we are aggregating models together, and that's where we can try to apply homomorphic encryption. So essentially, the local model parameters as such, we need to protect them using this homomorphic encryption, send it to the federated learning server. Now the fusions will completely happen in cipher space, and will so the models will be averaged and then sent back. Again, I will run decryption, and then once with the decrypted model, I can do normal federated learning. So essentially, we are protecting the updates of the model which were shared over the network, and homomorphic encryption can be used for protecting them. And the last about the integrity. So essentially, when we are trying to run any models in our system, at a compiler level or at operating system level, the data is often worked as in plain text. So there are hardware backed systems such as Intel's. Uh, so over here, when we have this Intel's XG Guard, or the confidential computing platform which is there, we could use their secure enclaves, which provides us the hardware level attestation of the code is not tampered with, and the data transfer is also secure. So only the place where the model will be actually in an unencrypted format would be inside the secure enclave, and there we will be running a tested code, so that also cannot be tampered with. So essentially, applying it to federated learning, we could apply this to do trusted execution of the aggregation level, or we could try to do trusted execution in the local training as well. Right now, considering the amount of computation required or the complexity required for training using trusted executions, it's well suited for moving the federated learning, the fusion algorithms into an enclave, rather than moving the training in the enclaves. But both of these are possible, and essentially, when we are trying to do it, we are protecting uh, the integrity of execution. So every participating party is following the exact same process of training, as well as the aggregator server, which has access to the updates from all these local models. They're trying to they cannot misuse the updates which are given and use it for any other purpose apart from federating it together. So that covers, in short, the I had to run through because of limitation of time. But essentially, these are the techniques which are used for making trying to train models on sensitive data and protecting the privacy of sensitive data. Thank you. Rattaraj Mukta, maybe we could take some questions as they have come now.
Yes, I think, yeah, Dataraj. So I was just planning to start the Q&A from the Q&A tab first. Let us start taking the questions from the tab first, and then we will move to chat. Dataraj, do you want to take it up? First one is, I think, already answered. Uh,
Perhaps you could choose some questions of major interest, and then go to the other questions later once we break the session. I mean, once we complete the session, like people who are interested can ask questions after the session also. Could you hear me?
Yeah,
Sorry.
yeah.
Yeah.
That we can't hear you.
Dattaraj, I guess you're on mute. No, we are not able to hear you, Dattaraj.
Okay. So I think meanwhile, while the Dattaraj is joining, maybe that Amog, there is a last question on the chat, which is about FL, and essentially, Abhijit is senior research fellow. He is trying to ask how does explainability work for FL. Do you want to take that up?
Sure. So essentially in federated learning we are trying to train models in the same way as how they were trained traditionally. So the model files as such are same as what we would have got in traditional machine learning. So once the model files are available, we could try to run explainability algorithms the same way as they were run for traditional machine learning.
There's
Dattaraj,
another
yeah.
question, Amog, related to federated. I think meanwhile Dattaraj is joining. How much is performance difference when comparing data sharing, non-secure versus federated learning? This is the question from George Ose from Walmart Global.
It's a very good question, George. Uh, So, in when we are trying to see federated learning versus an aggregated way, uh, the difference actually comes in with respect to the data size. So, if we have a really, so we have to think about it as same as partition data. So, if we were try to partition this data in such a way that uh, we have uh, we have a lot of data available at every party. They will actually try to balance each other out, and we'll get an overall accuracy which is kind of which matches with what we could have got at aggregated way. But essentially, if suppose there is a party which has uh, lot more data than the others, then what happens over here is that there is a push pull effect, and we see some performance drops which are there. So in our experiment, what we have observed is that uh, in case the non-aggregated model, or sorry, the aggregated model could give us somewhere around say 88% accuracy, then in a federated learning way, when we partition the same data, we could get somewhere around 84. So we could see roughly around uh, 4% drops in scenarios wherein the data can be partitioned well. But in scenarios wherein the data is like there is a lot of imbalance between each parties, then every experiment varies, and we observe variations in the performance which are there. But in general, because it's a decentralized technique, there is a performance drop as compared to what we could have achieved with aggregated setting.
Thank you, Amog.
Hey, can you hear me now?
Yes,
Yeah, Dattaraj, you're audible.
Okay, sorry about that. Uh, yeah, so I think we'll just go, like Ramana said, Mukta, between the three of us, we'll just pick up some questions and we can start, right?
Yes, yes. So let me read out. So I think one of the question that I really wanted answer from you was about what about other types of biases such as geospatial distributions of samples? It was though partially answered, but this question has come
Mhm.
from Nanda Kumar.
Yeah, that's a very good question. And yeah, so, and I'll try to attempt to answer, and maybe you can join in,
Yes,
Mukta. So
sure.
basically, yeah, I think geospatial definitely will be, in my mind, this is a valid bias we have to consider. I guess it gets back to the problem at hand. I mean, if there is a if there is a geospatial element that the data in different regions would be treated differently, then you may actually want to consider it while building the model. In fact, in some cases, if the data is too disparate, you would want to build a specific model for a geospatial location or for a boundary. So I guess it goes more around. You definitely want to evaluate the bias by getting the geospatial data, maybe using a geospatial boundary library to figure out how the basically when you want to evaluate bias, you divide the data into groups. In case of gender, it is very straightforward, male, female. But in geospatial, you would want to create the groups. So based on your domain, if you have a straightforward problem like Asia versus North America, then you can do the geospatial separation. But if it is more granular, you would want to use a geospatial library to make sure your groups are separate first based on domain, and that is not, that would totally depend on the problem statement. And then you evaluate using the same libraries. You can use the same libraries like IBM AF360 to see if within those bands there is a bias, and then either decide to have a separate model for these geographies or some way to mitigate the bias. So I would say figuring out those geographies would be the main problem here, but rest after that it remains the same problem. At least that's what I think. What do you think, Mukta?
Yeah, I completely agree. And I think this answer is partially catering to another question asked by Saurabh. He asked the question as, isn't bias more
Mhm.
subjective and should be application dependent? Exactly, that's the point that Dattaraj was trying to tell. The bias is highly dependent on the application in hand and the problem of prediction, classification, clustering. What is the problem, the ML problem that we are trying to solve? So he was kind of mentioning in the question that discrimination can be, so the example that Dataraj you showcased here, his point was maybe in the unbiased model towards the gender,
Mhm.
the bias could come due to the education background, since that comes up as the second important variable. But I think just to answer that, you are telling it, we need to figure out whether there is a bias in the system with respect to the variable that you are interested into at this moment, and that is scattering or hampering more so for the problem at hand. Once you identify that there is a bias, then you will take the next step, how to mitigate it, depending on if you feel that is a requirement for the kind of model you are building.
Yeah,
And I think this is catering to both the questions, in summary, that Dattaraj and
yeah,
has given the answer
absolutely.
on. I think let's move to one of the other question that has come from Sai Manikanta. The question is, what is the best approach to calculate the concept drift and data drift?
Yeah, so data drift, I would say, is more easier, at least relatively, because there you are looking at just data distribution. So you could use any of the statistics techniques, any of the sampling techniques, or you just pure statistical testing to see if there is a drift that is happening. Or you could you just visually look, like in our example, we just saw it with with some charts to see if there is a drift happening. Concept drift becomes a little difficult because for concept drift, then you will have to know the actual the labels, the ground truth, because many times in field you don't always have the ground truth, or you don't have a provision to feed the ground truth back to your algorithm or to your model. So concept, if you have a way, either manually or through some mechanism to get the ground truth, like once the loan is approved, you want to know that the actual loan was approved and it was not defaulted. So that mechanism, if there is a way, in that case, if you have ground truth, then concept drift is pretty straightforward. You calculate the accuracy, and at one point, when the accuracy drops, you can just say that there is a change in the relationship between the x's and the y's, and there's a concept drift. For data drift, there are a couple of very good libraries. One is Alibi Detect that we talked about, and then there's another library from a startup called Evidently.ai. It's very good that it compares two data frames and gives you a data drift. It does all this standard tests, like there's a KS test for categorical data, and then there's one more, I think, chi-square test for continuous data. So both the statistical tests it does, both Alibi and Evidently.ai, and it can give you the it can give you statistical measures if there's a data drift happening, and same thing for concept drift.
Thank you, Dattaraj. I think that gives a very good answer to the question. I see, and I'll read out the next question that has come from Pavan. How to overcome lack of coordination and improper handoff between the data scientist and operations teams, which can lead to delays and errors using MLOps. I think this is a very good question, and that is why we always promote and always suggest that we should have ML ops end-to-end pipeline putting up into the system whenever we are developing this ML system. Over to you, Dattaraj.
Yeah, absolutely. And a lot of these patterns that we talked about, they can help you mitigate, like a data catalog or especially the model registry, that both teams are taking the same model. You are pushing the model and the same model is being used, but then rather than emailing models or loading it to a shared folder or something, but then that so much tooling can do. I mean, it is more of a culture thing where just like now DevOps has been so matured that development or operations teams are working so close by. I think the same principle, the same tooling could use Jenkins and similar Jira to log cases. I think the tooling can be the same, but it's more of a culture shift. You need to make sure that ML development teams and your model monitoring and operations teams need to work together and set the same principles. So absolutely, I mean, it will be more of a culture shift, but I think with the right tooling, you can get it started well.
Yeah, thank you, Chaturaj. I think the next question, I can take that up. It's pretty simple. Is there a standard way in defining privileged and underprivileged group? So I don't think so. There is a standard way. Definitely, it will dependent on the problem at hand. Basically, what kind of a problem. So if it's a classification problem, just in the example and the other question that I was talking about, gender seems to be an obvious choice for underprivileged group, but this is not the case always. You might find that the problem statement is so that education or the age becomes a underprivileged group, and that's where these fairness metrics are more important when you define what is a fair system. And the AI ethics committee comes into play here as well, that a priori we need to define that this is what we are wanting to call it as a fair system in respect of the problem at hand. And I don't see there is any standard way of defining this privileged and underprivileged group. Now, before I take up any more questions, I would want to have a quick time check with Rama.
I think we can probably go on for like 5 more minutes. Any other important questions? And then we have a sponsor video to be played. So, any other important questions that you think need quick addressing, just you can do it now. And then the other questions you might want to take them offline. Yeah.
Correct. So I
So
just see a couple of, yeah, Mo, go ahead.
Yeah,
That's what I
so
was coming into.
I see a question which asks, I think it's by Abhinav Pachori. What's the difference between differential privacy and homomorphic encryption? So, the short answer to that is differential privacy is a technique wherein we apply noise and we obfuscate the data so that when we are trying to train models, we essentially are working with unencrypted data, but we are obfuscating it or tempering with it a little bit so that an individual data point in raw format is often not found at, or it's not shared, or even if suppose somebody tries to reverse engineer it, they don't get to the actual data point, they get to a perturbed or a obfuscated data point. In homomorphic encryption, what essentially we are doing is that we are applying encryption technique to go to a cipher space, so the data is completely encrypted. And there are techniques for trying to build models on homomorphic encrypted data, but in federated learning, often that's not followed. Essentially, what we do is that we are just encrypting the parameters which are being shared to the server, and just those operations are what is happening in the encrypted space. So I hope that clears the question.
yeah, so one question I think I just missed, and I'll take up one more from Avinash Venugopal. It's could you please provide an overview of how bandits are being used to support the reproducibility plus transparency pillar? So I talked a little bit about that in the presentation. So bandits basically is a selection problem where you have multiple decisions to make, and you select. It's like the slot machine, like one arm you choose and figure out what reward. So typically, bandits come into play. At least that pattern is used heavily in the deployment area. Like earlier, it was pretty much A/B testing. You would spend so much time for one model or a particular customer base with one model, second customer base with model B, and compare the responses. But then that would let you spend a lot of time with an underperforming model for a customer base. So bandits help you with that. So if you use something like a multi-arm bandit, there are algorithms like Thompson sampling which can reduce the regret there. Which what they can do is they can make sure the minimum amount of time is spent on an underperforming model, and most of your customer base gets the better performing model. So that is where the bandits algorithm comes into play. And tools like Seldon, let you support that. So it can automatically, all you have to do is specify the multiple bandits, 3 or 4 models you want to experiment with, and it will take care of that, either epsilon greedy or Thompson sampling, whatever the contextual bandit strategy is. It will use that to deploy the model to the right audience and get feedback from them. So yeah, so that's how typically bandit pattern is used for your reproducibility and transparency. I think there was one more for federated learning, Amok, just recent one on wireless networks.
I guess we are running out of time. I'll answer that
Okay,
question on chat, I guess.
okay. So I think
Okay, wonderful. So many thanks to the presenters for their excellent presentation as well as uh, patiently answering the audience questions. If for the audience, this video is being recorded. Hopefully, with the consent of the presenters, we may be able to share the slides publicly later after the sessions are over. Uh, at this point, I would also like to thank the sponsors. We have a set of excellent sponsors who've helped us with this conference. So can we have the sponsor video for this session? Thank you. So others could have their questions answered offline after this. Thank you.
I'm Jamie Tevan, Chief Scientist at Microsoft, and I'm excited to share a little bit about what the latest science is teaching us about how work has changed. I'm going to talk a little bit about the research that we've been doing at Microsoft into remote and hybrid work. And I think that the conference that you're attending today is a great example of this. You know, you're spending a lot of time focused on in-person events in Bangalore, but you're also hearing virtually from me and other speakers from around the world. And, you know, we've learned a lot about remote work in the past 2 years. We've learned a lot as individuals about how to sit in remote meetings all day without getting completely exhausted, or how to take advantage of being at home to have lunch with your family or to take a nap. But as a company at Microsoft, we've also learned a lot about how digital technology can support remote work. And you can see our products have really changed significantly since March 2020. Interestingly, the current moment feels a little similar right now to how it did back in March 2020, in that we're not exactly sure what work is going to look like in the coming months. Only now, with workplaces starting to open back up, instead of remote work, it's this new thing called hybrid work that's the big, scary unknown. And it is actually surprisingly scary to think about giving up remote work, as much as I can't wait to return to the office. I mean, I'm really excited to interact more with people in person, but I also don't want to give up my sweatpants or return to commuting. And we see these contradictory desires, which our CEO Satya Nadella calls the hybrid paradox. We see them in the data. So for example, in a survey that we ran with 30,000 people across 31 countries, 73% of people said they wanted the flexibility of remote work to stick around post-pandemic. But at the same time, 67% of those same people in that same survey said that they wanted more in-person time with their colleagues as well. And so the good news is that research is great for making sense of these apparent contradictions. So for example, I recently published a large-scale study with Long-Chi Yang, Sid Suri, Sonia Jaffe, and a bunch of others in Nature Human Behavior, where we looked at the collaboration patterns and how they changed following COVID. So the study compared the anonymized collaboration patterns of two groups. One was Microsoft employees who worked remotely before the pandemic, and the other was employees who shifted to work remotely during the pandemic, and that was a total of 61,000 people. And because the collaboration activity of these two groups moved in parallel prior to the pandemic, we could use causal analysis to subtract out any differences in behavior between the two different groups and isolate the effects of remote work from the effect of the pandemic. And one of the first things that jumped out of the data was that remote work caused a 5% decrease in synchronous meetings. This is counterintuitive because many of us have spent more time in virtual meetings during the pandemic. But after removing the effects of the pandemic via causal analysis, we see that remote work didn't actually drive more meetings. It drove more email and it drove more IM messages. It drove more asynchronous collaboration. And this seems awesome. I mean, who wants more meetings? Asynchronous collaboration, it's flexible. It makes it easier to collaborate across different time zones and different working hours. But prior literature also suggests that synchronous collaboration is where we align and where we do meaning making. And so we need to figure out how digital technology can bring more of this meaning making into our asynchronous collaboration so that we can actually get the best of both worlds. And you see people starting to do this already by, for example, turning on meeting transcription and recording the meetings when they meet, which increases the accessibility of the content to both synchronous attendees as well as asynchronous attendees. Another thing that the study showed, which in this case is actually consistent with the correlational trends, is that while firm-wide remote work increased the intra-group connections, people's strong ties, the share of time that people spent with cross-group connections or their weak ties dropped by about 25%. Teams are essentially adapting to do more loosely coupled work while remote. They were working in these tight-knit groups with fewer dependencies across group. But because weak ties bring people new information, it's going to be really important that we create proactive ways to ensure that people continue to build broad networks. And so I really want to put a call to action out to this community to think about how your research applies broadly to the significant disruption in work practices that we're all living through right now. As data continues to be created and used at scale across all aspects of our lives, data science is the mechanism that allows us to transform that data into insights. And I think it really behooves us all to think about what we can learn in the research that we do about people's productivity practices so that we can intentionally create a new and better future of work. For more about the research that I've talked about today, check out the New Future of Work website. From there, you can get to the Microsoft research site and explore the full range of research happening at Microsoft. Thank you.
Okay, thanks all. That ends the first tutorial. So we'll see in tutorials 3 and 4. So yeah, thank you. So
Thank
any
you,
other
everyone.
questions, you could contact the authors, the presenters later.
Thank you. Bye.
Thank you.